The discovery of Kepler 452b in 2015 marked a watershed moment in exoplanet research. NASA's announcement described it as Earth's older, bigger cousin. So, a rocky world orbiting within its star's habitable zone. Yet beneath the optimistic headlines lies a fundamental challenge that aerospace medicine has only recently begun to address. The most promising habitable exoplanets we've identified are super-Earths, worlds with surface gravity up to twice that of our home planet. To understand the significance of this challenge, consider the human cardiovascular system. Your heart evolved over millions of years to pump blood vertically against Earth's 1G gravitational field. On a super-Earth with 1.5 to 2 times Earth's gravity, that same heart would struggle to deliver oxygenated blood to your brain. The result, according to research published in the Journal of Gravitational Physiology, would be immediate orthostatic hypotension. In simpler terms, you would lose consciousness within minutes of standing upright. This presents what aerospace engineers call a biological constraint problem. We've spent decades developing the technology to reach distant worlds. The James Webb Space Telescope continues to identify potentially habitable exoplanets. Yet we've devoted comparatively little attention to a critical question. Can unmodified human biology survive on these worlds? Drawing on peer-reviewed research in gravitational biology, recent advances in CRISPR gene editing, and NASA's own studies on long-duration spaceflight adaptation will explore how humanity might engineer itself for life beyond Earth's comfortable 1G environment. The challenge of high-gravity adaptation has roots extending back to the earliest days of human spaceflight, when Soviet cosmonaut Yuri Gagarin completed his historic 108-minute orbital flight in 1961. Medical teams immediately noted cardiovascular changes upon his return. The Apollo astronauts of the late 1960s and early 1970s experienced similar effects, what NASA termed cardiovascular deconditioning. These pioneers had spent mere days in microgravity, yet their bodies had already begun adapting away from Earth's 1G environment. The inverse problem, adapting to higher gravity, received less attention until the 1990s, when exoplanet discoveries accelerated dramatically. In 1995, astronomers Michel Mayor and Didier Queloz announced the first confirmed exoplanet orbiting a Sun-like star, 51 Pegasi b. This discovery opened a new era. By 2009, NASA's Kepler Space Telescope began its systematic survey, ultimately identifying over 2,700 confirmed exoplanets before its retirement in 2018. A pattern emerged in the data. The most common type of potentially habitable world wasn't an Earth twin. It was a super-Earth. These planets, with masses between 1.5 and 10 times Earth's mass, appear frequently in the habitable zones of their stars. Kepler 452b, discovered in 2015, orbits a G-type star similar to our Sun at a distance that could permit liquid water. However, with an estimated mass 5 times that of Earth, its surface gravity would be approximately 1.6 to 2 times our own. The biological implications became clear through research conducted aboard the International Space Station. Since 2000, astronauts have participated in studies examining how the human body responds to altered gravitational environments. Dr. Michael Barrett, a NASA flight surgeon and astronaut, noted in a 2018 interview with Space Medicine Journal that the cardiovascular system is exquisitely sensitive to gravitational loading. His research demonstrated that even short-term exposure to increased G-forces during launch and re-entry produces measurable stress on the heart and circulatory system. The technical challenge is quantifiable. Human blood has a specific density of approximately 1.06 grams per cubic centimeter. In Earth's gravity, your heart generates sufficient pressure, roughly 120 millimeters of mercury systolic pressure, to overcome the hydrostatic column of blood from heart to brain. On a 2G world, that pressure requirement effectively doubles. The heart must work significantly harder, or the system fails. This physiological reality, combined with the prevalence of super-Earths among potentially habitable exoplanets, has driven recent research in two directions: genetic modification of human biology and technological augmentation through medical devices and protective equipment. Both approaches draw on decades of aerospace medicine experience, from the high G-tolerance training of fighter pilots to the countermeasures developed for long-duration spaceflight. When we talk about settling a habitable exoplanet that happens to be a super-Earth, the question is no longer abstract. It becomes an engineering problem in human biology. The environment sets the load. Our task is to determine whether the existing human design can operate within that load, or whether it must be modified. 1. The cardiovascular load, pumping against 2G. The first hard limit is the heart. In aerospace medicine, vertical G-forces are denoted as plus GZ, feet down, head up. Fighter pilots routinely experience plus 5 to plus 9 Gs in short bursts, but only with anti-G suits and specialized breathing techniques. Sustained exposure is another matter entirely. On a super-Earth with twice Earth's gravity, every column of blood in your body effectively weighs twice as much. The hydrostatic pressure difference between your heart and your brain increases accordingly. Research summarized in the journal Aviation, Space, and Environmental Medicine shows that unprotected humans begin to experience visual grayout around plus 3 Gs and loss of consciousness shortly thereafter. At a constant 2G, the heart must generate significantly higher arterial pressure simply to maintain consciousness while standing. Over years, this implies chronic left ventricular hypertrophy, thickening of the heart muscle, similar to what cardiologists observe in long-standing hypertension. The trade-off is clear. Either we accept a much higher baseline risk of heart failure, or we modify the system through genetic, pharmacological, or mechanical assistance to handle the load. 2. The skeletal system. Wolff's law under stress. The skeleton responds to mechanical loading through a well-established principle known as Wolff's law. Bone remodels in response to the stresses placed upon it. Astronauts in microgravity lose 1 to 2% of bone mineral density per month in weight-bearing bones. In higher gravity, the effect runs in the opposite direction. Chronic loading stimulates increased bone density and strength. However, this adaptation has limits. Modeling studies in biomechanics suggest that doubling body weight, as effectively happens at 2G, increases joint reaction forces beyond the safety margins. For cartilage and trabecular bone, particularly in the hips and knees. Everyday events, a misstep on a stair, a minor fall, would deliver impact forces that exceed what our current bone geometry was optimized to handle. From an engineering perspective, the solution space includes two options: redesign the structure, shorter limbs, thicker cortical bone, broader joint surfaces, or reduce the load per unit area through assistive devices. Both approaches change how we think about normal human proportions on a high-gravity, habitable exoplanet. 3. Muscle and locomotion. From sprinters to load-bearers, muscle tissue, unlike bone, adapts relatively quickly to increased demands. Resistance training on Earth can increase muscle cross-sectional area by 10 to 20% in months. Experimental myostatin inhibition in animals has produced 40 to 60% increases in muscle mass, although human trials have yielded more modest gains. On a 2G world, however, baseline walking becomes mechanically equivalent to uphill loaded marching on Earth. Metabolic cost studies show that energy expenditure rises roughly linearly with both speed and load. Daily life, climbing stairs, carrying equipment, would push unmodified humans into near-athletic levels of exertion for routine tasks. The design trade-off becomes apparent. Stronger, bulkier muscles improve mobility and reduce fatigue, but at the cost of additional body mass, which in turn increases the gravitational load on joints and the cardiovascular system. Any serious proposal to settle a high-gravity habitable exoplanet must balance these interdependent systems rather than optimizing one in isolation. 4. The engineering envelope of the human body. Engineers define an operating envelope for aircraft: speed, altitude, and load factors within which the vehicle can function safely. Human physiology has an envelope as well. Current data from bed rest studies, centrifuge experiments, and pilot training suggests that birth-normal humans can likely tolerate something close to 1.5 G for extended periods, with substantial but manageable health risks. Beyond that, the margin narrows quickly. This is the crux of the issue. Super-Earths in the habitable zone may be common, but only a subset will fall within our unmodified biological envelope. For the rest, if we wish to call them truly habitable exoplanets in a human sense, we must either redefine human or rely heavily on technology. The question of adapting humans for high-gravity habitable exoplanets divides the scientific community along disciplinary lines. Each perspective reveals different constraints, possibilities, and ethical boundaries. The geneticist's perspective, engineering the genome from a molecular biology standpoint, the tools for targeted human modification already exist. CRISPR-Cas9 gene editing, refined since its development in 2012, allows precise modification of specific genetic sequences. The technical pathway is relatively straightforward. Identify genes that regulate bone density, muscle growth, and cardiovascular capacity, then modify them in embryonic cells before development begins. The most cited example is myostatin, a protein that limits muscle growth. Natural myostatin mutations in cattle have produced the Belgian blue breed, animals with approximately 40% more muscle mass than typical cattle. Similar mutations occur rarely in humans. Documented cases show individuals with exceptional strength and low body fat. Dr. Sejin Lee's research at Johns Hopkins University demonstrated that myostatin inhibition in mice produces dramatic increases in muscle mass without apparent health penalties. For bone density, researchers have identified multiple genetic pathways. The LRP5 gene, when mutated in specific ways, produces unusually dense bones resistant to fracture. But 2002 study in the New England Journal of Medicine documented a family with this mutation. Individuals who had never experienced a broken bone despite significant trauma. The challenge isn't technical capability, it's prediction. Modifying a genome produces cascading effects throughout development. A change that strengthens bones might also affect calcium metabolism, kidney function, or vascular calcification. The human body is not a collection of independent systems, but an integrated whole. Optimizing for one environment, high gravity, may create vulnerabilities in another. Earth normal conditions, or microgravity during transit. The aerospace engineer's perspective. Mechanical augmentation engineers approach the problem differently. If the biological system cannot handle the load, provide external support. This philosophy has driven decades of development in powered exoskeletons, originally designed for military load-bearing and industrial applications. Modern exoskeleton systems, such as those developed by Exobionics and Lockheed Martin, can reduce the effective load on human joints by 50 to 70%. For a high-gravity habitable exoplanet, the concept extends further. A full-body support system that bears gravitational loads continuously, not just during heavy lifting. The technical precedent exists in aviation. Fighter pilots wear anti-G suits, pneumatic garments that compress the lower body during high G maneuvers, preventing blood pooling and maintaining consciousness. A super-Earth colonist might wear a similar system continuously, with graduated compression that adjusts based on posture and activity level. The limitation is energy. Current exoskeleton batteries provide 4 to 8 hours of operation. For continuous use over years, power requirements become substantial. Solar charging, radioisotope thermoelectric generators, or biofuel cells all present trade-offs in weight, safety, and practicality. The physician's perspective. Long-term health consequences. Medical professionals focus on what happens after adaptation, the chronic health outcomes over decades. Dr. Michael Barrett, who spent over 200 days in space, has emphasized that we don't fully understand the long-term consequences of altered gravity on human health, even in the microgravity direction. High-gravity environments would likely produce chronic cardiovascular strain, accelerated joint degeneration, and altered endocrine function. The comparison often drawn is to obesity. Carrying excess weight produces similar mechanical loading and cardiovascular stress. Epidemiological data shows that sustained high body mass loading correlates with earlier onset of osteoarthritis, heart disease, and metabolic syndrome. Pharmaceutical countermeasures could address some risks. Beta blockers might reduce cardiac workload. Bisphosphonates could slow bone remodeling. Anti-inflammatory medications might protect joints. But long-term pharmaceutical dependence creates its own complications, side effects, drug interactions, and supply chain vulnerabilities on a remote, habitable exoplanet. The evolutionary biologist's perspective, speciation, and the no-return scenario. Perhaps the most profound perspective comes from evolutionary biology. If humans settle a high-gravity world and adapt, whether through genetic modification, natural selection over generations, or both, they will diverge from Earth-based humanity. The precedent is clear in Earth's own history. When populations become geographically isolated and face different selective pressures, they diverge. The timescale varies, but reproductive isolation can occur within thousands of generations for complex organisms. A human born and raised on a 2G habitable exoplanet with genetic modifications for high gravity tolerance would face serious health risks if they returned to Earth. Their cardiovascular system, optimized for higher pressures, might produce dangerous hypertension in 1G. Their denser bones and more massive musculature would be metabolically expensive to maintain without the gravitational loading that justified them. This creates what evolutionary biologists call a fitness landscape problem. The optimal phenotype for one environment is suboptimal, potentially dangerously so, for another. Space colonization, in this view, isn't just geographic expansion. It's the beginning of human speciation into multiple branches, each adapted to different gravitational regimes. Earth-normal humans, Mars-adapted humans with elongated limbs and reduced bone density, and super-Earth humans, built like biological tanks. The question then becomes not, can we adapt, but are we willing to accept permanent divergence as the price of settling habitable exoplanets? The settlement of high-gravity habitable exoplanets represents more than a technical challenge. It forces us to confront fundamental questions about human identity and adaptability. What emerges from analyzing cardiovascular limits, skeletal mechanics, and genetic modification is a singular conclusion. Unmodified humans cannot comfortably inhabit super-Earths with gravities significantly above 1.5 G. The engineering envelope is too narrow, but this doesn't render such worlds uninhabitable. It simply means human must be redefined for each gravitational context. The path forward likely involves hybrid solutions. Initial colonists might rely heavily on exoskeleton support and pharmaceutical interventions. Subsequent generations could incorporate targeted genetic modifications, denser bones, enhanced cardiovascular capacity, optimized muscle fiber composition. Over centuries, natural selection would continue the work, favoring traits that improve survival and reproduction in high gravity. This raises the prospect that future humanity will not be a single species, but a family of related subspecies, each adapted to different worlds. Earth humans, Mars humans, and super-Earth humans might remain interfertile initially, but genetic drift and continued adaptation would eventually create reproductive barriers. From an evolutionary perspective, this is neither unprecedented nor inherently problematic. It's simply how life responds to diverse environments. But it challenges our cultural assumption that humanity is a fixed category rather than a flexible one. The critical question isn't whether we can adapt humans for high-gravity worlds, but whether we should, and under what framework of consent and governance. Modifying embryos creates individuals who never chose their adaptations. Engineering humans for environments they cannot leave raises questions about autonomy and irreversible commitment. These aren't problems with purely technical solutions. They require international cooperation, ethical frameworks, and long-term thinking that extends beyond quarterly budgets or election cycles. In practical terms, the next century of space exploration will focus on lower gravity targets. The Moon, 0.16 g, Mars, 0.38 g, and orbital habitats where gravity can be tuned through rotation. These environments let us develop the biotechnology, social structures, and ethical frameworks needed before confronting the harder problem of super-Earths. But the theoretical work must begin now. Understanding the limits of human adaptability and the tools available to extend those limits will determine which of the thousands of discovered exoplanets qualify as genuinely habitable for our descendants. The universe offers many worlds. Whether humanity can inhabit them depends less on the planets themselves than on our willingness to change what human means.